Hi, I'll be presenting the paper Dragon, a lightweight, high-performance distributed stream processing engine. My name's Aaron Harwood, and my collaborators are Maria Rodrigues-Reed and Gayashan Nirashana Amarasinghe, uh, and I'm from the University of Melbourne, Australia. So we've been working with stream processing for some time now, largely with social media data, such as data from Twitter, but other forms of data now as well from forums and so on. And we've been very interested in doing things such as tracking discussions on topics as they evolve and being able to potentially respond to those discussions in a timely way. So kinds of applications that we're interested in are effectively real-time applications, event detection, and being able to respond to that. For example, emergency services or police looking at social media information and trying to decide whether they need to respond and then be able to do something quickly within the time frame that would be useful. And stream processing is the paradigm that one applies to do that, as opposed to batch processing, where you may well be looking at processing 6 months worth of data in one batch to gain information from it. We're really looking at each piece of information that comes to us, each tweet or each forum post, as quickly as it does come, as soon as it comes, being able to absorb it, to process it, and lead to a result that someone can then an operator can be looking at and make a decision about. So I guess for over 5 years, 6, 7, 8 years, perhaps we've been doing this, and we started working then with the system Apache Storm, which was fairly new at the time for stream processing. You may or may not know it was developed by Twitter, the company, and then they open sourced it. Interestingly, the same company later developed Apache Heron, which took the same API as Storm, and but rewrote effectively the engine for it. And so one could take an application written for Storm and simply recompile it in principle on the Apache Heron platform. And these two platforms have two different goals in mind that are fundamental to these systems when it comes to performance. One is minimizing latency, the time that it takes for data to get through the system, for a new piece of data entering the system to get through the different components and be processed effectively. And that's Apache Storm, which is focused on minimizing the latency of these processing pipelines, if you like. And Heron, on the other hand, has looked at throughput and processing large volumes of data, but still in a real-time system. It's just that it is not necessarily doing everything that it could do to reduce latency. As you know, there's a trade-off. You want to reduce latency, you necessarily end up reducing the throughput, which you'll see in this. Storm has managed to reduce latencies to sub-milliseconds for intercomponent tuple transmission, which is very low compared to other platforms. So there are other stream processing platforms like Flink and Spark and so on that do stream processing that we are looking at as well. But in this paper, we have compared to Apache Storm and Apache Heron, because the system that we have developed, our stream processing platform, uses the same API as Storm as well. So just to look at some of the basic definitions of a stream processing system using the nomenclature that, say, has been proposed by Storm. So an application is a set of components effectively, and they're categorized in Storm as either spouts or bolts. The spouts are essentially the sources of data. They don't have any incoming data streams to them. They generate data, but they generate data potentially by connecting to an external source, like Twitter, for example, the streaming API of Twitter, or any other API on the web that produces data, and converting that into streams for the system, which they emit. Bolts, on the other hand, receive streams and may or may not output streams. If they don't output any streams, then they're considered a sink of data, but they do processing as well. So they're essentially the processing elements. So for parallelism in these systems, each of these components can have any number of identical instances that are treated in the same way. It's the same code that's running, and that produces the parallelism. So for any two components, there can be one or more declared streams from A to B, and then an instance of a spout or bolt is said to emit data onto a stream, or a tuple, like emit data as a sequence of tuples, and those tuples have a number of declared fields. And then each stream is declared with a grouping, so it might be an all grouping, a shuffle grouping, a fields grouping, that determines the exact instances in the receiving component that receive the tuples that are on that stream. In fact, the grouping is not just per stream, but per endpoint. So we have in the paper developed a bit more of a graph model to describe this, and many authors may just use simple directed graphs to describe these kinds of stream processing applications or to model them, but we've seen, and we show here an example that that these contemporary stream processing systems are effectively modeled by a multi-directed hypergraph. Usually cycles aren't allowed in the stream processing systems, although they all today, the modern systems are practical systems that sort of allow some kind of cycles, maybe not completely supported cycles, but some kind of cycles for iterative algorithms and other things like that. But in this figure, you can see a number of components and some streams, which are the edges here that have a single source, and then but potentially multiple endpoints. Each one of those endpoints ends on a component, and the endpoint has a particular kind of grouping that says, for the instances, say, of component 4, and there may be several instances of this component 4 in parallel, how do those instances receive the tuples that are sent to that component? If it's a shuffle type grouping, then it means that one of the instances will receive the tuple, and it's typically used to load balance over the instances. If it's an all grouping, in this case down here for C3, then it means all of the instances will receive the tuple. And you can see that, so this one stream coming out of component 1 is being received by 3 different components with different groupings. A component can be receiving multiple different streams of information, either coming from multiple components or even from the same component. So there's 2 streams coming from component 1. And we can have as well custom groupings that are defined effectively by the application programmer to be very specific about when the tuple is emitted to which instance of a downstream component that's listening to this stream does that tuple go. Building a stream processing engine today is about building a system that can support this model of communication. We have recently, I guess over the last year, built an open source stream processing platform. I can quickly have a look at it here. I have it, the web page to our GitHub repository. It's a fully fledged system that uses the same API as Storm and Heron. Some minor differences. It's not completely covering all of the API. It's really just covered the parts that we've been using over the several years now to do our stream processing. So we developed that recently. One of the things is that it's very lightweight. It's only 7.5 megabytes of installation space required to sort of install it on a node, if you like, in a cluster or on a device. And indeed, because it's lightweight, we've looked at it running it on Raspberry Pis and other low resource devices like that. As opposed to Storm and Heron, which have gone to be quite heavyweight and often depend on other third-party resources like Zookeeper, perhaps, to manage the devices that they're running on. So this is one sort of byproduct of developing it. And so in the paper, we're going to show some experiments where we compare our platform with Storm and Heron. And overall, just a sort of an overview that we do have a fairly favorable comparison as a sort of all-rounder type platform in that the throughput characteristics are near to that of Heron, and the intercomponent latencies are less than 10 milliseconds under high load, which can be is better than Heron. So the maximum latency is significantly less than Storm's under high load as well. So there's some interesting things about the way our platform works in comparison to these two systems, which, as I said, are two different ends of the scale of either trying to maximize throughput or minimize latency. So there's a lot to say about building an open, a stream processing engine from scratch. But the key aspects, I guess, are concerned with the way in which the queuing is done and the way in which data is passed from one processing element to another, from one bolt to another, or from a spout to a bolt, so on. And so, for example, in Storm's most recent system, there's a lot of emphasis on lock-free queues. And therefore, if queues are going to be lock-free, that means that you need to make sure that your queues don't ever fill up. If you don't want to lose data or just throw data away when you try to offer to put things onto a queue. And so, the very original Storm implementation had a kind of system where it was using lock-free queues. It was just offering data to put it onto a queue. And if the queue was full, then it would just drop the data. And then it had a way of timing out such that if a tuple needed to be replayed because it was lost, the system could do that. That really wasn't the way that we needed the system to work. So that was one of the motivating factors for building our own system, our own engine to do our stream processing. Heron, on the other hand, uses blocking queues. Problem with blocking queues, of course, is that if you have too many context switches, then that can take place, and that can hinder the performance. So that Heron does use a single thread per process model. So each of the bolts and spouts will be on a process of its own, whereas Storm will allow multi-threading. Now, what we've done is we have a multi-threaded system, and we do use blocking on most of the queues in our system, but we do a few other things to try to ensure that the amount of context switching is quite low. And one of them is creating, for every tuple that's emitted from a bolt or a spout, we do have what we call a tuple bundle. And indeed, we're doing a kind of micro batching, a bit like Spark would do, I guess. There's a micro batching of tuples. We do create small batches, and the reality is that if you're going to use blocking approaches, and indeed when you get to the network and you're going to transmit data that to do so efficiently, you have to have some amount of bundling of the tuples, especially considering that a tuple is a small amount of information. It might just be a word or a few characters. So tuples get emitted into a bundle. When that is expired or it's full, then the system for any other bolts that are on the so this whole box, if you like, represents one JVM, one Java Virtual Machine. For any other bolts that are on the same machine that is a destination of the tuples in that bundle, and I might add that all of the tuples in that bundle have exactly the same destinations, then it may well be it's offered onto those queues, which is a non-blocking offer onto the queue. If the queue is full, so that is that the offer fails, then it will put the bundle onto a local output queue, and that output queue is put onto a queue of queues, which another thread in the system or a couple of threads or a pool of threads is reading, that will later take those tuples, bundles off this queue and bring that across to the input queue whenever that it can. So there's a certain amount of non-blocking there, but this put must take place. That's a blocking put. And as well, we'll look at the destination, and if indeed some of it needs to go, so the destination of the tuples, which can be a set actually of different destinations that those tuples need to go to, needs to be over the network, then there's an output queue and it's put there as well. So there's a certain amount of blocking operations. There's a certain amount of non-blocking operations in Dragon. And you can see as well, there's when the network coming in, there's a queue coming in from the network that also goes onto this outputs pending queue that delivers tuples finally to where they need to go. There's a little bit more beneath in the network part of Dragon to handle the networking, but it's very similar to this outputs pending queue style, this part here that's kind of central to the way that it works. So we sort of, when we developed it, we have a kind of combination of blocking and non-blocking queuing style with some bundling of tuples to reduce context switching effectively when we're doing the blocking operations. So that's kind of Dragon's queue design. We ran some experiments, preliminary work, effectively we're reporting in this paper, which were run only on a single machine, but it was a machine with 24 vCPUs and 200 gigs of RAM. We also, though, did test it on Raspberry Pi, as I mentioned earlier. And we tested Apache Storm, we tested Apache Heron with these versions, which were the latest versions that we available to us, and we tested as well our system, the version of our system 003. So for a topology that we tested with, we had just 3 components. It's a word counting topology, so it has something that reads sentences. That's actually a spout. It reads sentences from a file and emits them on a shuffle grouping to one or more tokenized instances. So we did experiments where we didn't have any parallelism in the system, and we did experiments where we did have parallelism. When we had parallelism, we had 10 instances of the tokenizer and 10 instances of the counting bolt. So the tokenizer takes a sentence, splits it into tokens, and emits one tuple for each of those tokens. And then those tokens are then received by a count bolt, which is where the same token will always go to the same bolt. That's the topology that we used. For the data set, we have lots of data that we've been collecting over the years now. So we chose a data set of 45,000 short text social media posts. that were collected from all over the world. So they included all different languages in UTF-8 format and all different kinds of symbols and hashtags and so on. And we just considered each post as one sentence. And we had to increase that a little bit. So we ended up duplicating a bit of data for this data set. And then a little bit of statistics around the data set is the bytes used. If we looked at that, the mean bytes per sentences was 91 bytes of data in each sentence, about 15 tokens for each sentence, split into 15 different tuples. The way that we measured latency was that the sentence before that it was emitted, it was time stamped with a start time. And then when the sentence was tokenized by the tokenizing bolt, each of the tokens was the same start time was appended to that token. So every word, if you like, had the start time that was the start time for the sentence that it appeared in. And then there was an end time that was the time that the word was actually included in the count for that particular word at a bolt. So the latency was the end time minus the start time, and we measured that. That's for every word for all of the sentences. For throughput, we controlled the rate at which we emitted sentences into the system by having a separate thread that would read from the file, emit, and then sleep for a certain period of time, and then emit the next sentence, and then sleep, and then emit the next sentence. And then we would ramp that up and see and measure the system under different kinds of throughput, light throughput, medium throughput, heavy throughput, to sort of see how does its statistics change. So, for example, when there's no parallelism in the topology, we have the three systems, Dragon, Heron, and Storm. The first top three charts is for 1,000 sentences per second were given. And then in the second three, we had 2,000 sentences per second. And this shows over time, if you like, the token, so the delays just sorted in terms of token number in a particular bolt in the system. There was only one instance of the count bolt in this case, and showing the delay. There's a few things to note, perhaps. One is that, first of all, that you can see that the effective throughput, actually, we offered 1,000 sentences per second, but the throughput that we measured in terms of the total time it took to complete all of the sentences that we offered led to an effective throughput for Storm being a bit lower than Dragon and Heron. But when we look at the delay for Storm, and in both cases for the 1,000 sentences or the 2,000 sentences, it's quite a bit lower, and the next chart will show that a bit better. The 2,000 sentences per second show instabilities effectively in Dragon and Heron, where they start to things start to queue up, right? And so the data sits in the system for longer, and therefore the latencies get higher for each of the tokens. And indeed, for Dragon, it was disappointingly a bit bad, and we're starting to investigate more why, but where the latencies did get quite a bit higher in this case. But if we look at the statistics here, there are some nice aspects. And first of all, Storm does indeed get the minimum latency is indeed sub-milliseconds. Some of the tuples went through the system very quickly. Storm does a lot of work on ensuring that the queues in the system are close to empty all the time. And so throttling the input to ensure that when a tuple does enter the system, it will experience very low latency. Dragon did, its minimum latency was quite good. It was better than Heron, but its maximum latency was quite poor. In terms of course, of the effective throughputs, it was kind of near to Heron, but not quite as much as Heron. So it's kind of doing okay there. The next set of experiments we show here are when we had 10 tokenizer instances and 10 count instances for the parallelism. So in this case, we show again a light load of just 1,000 sentences per second being offered to the systems, but then we show now 10,000 sentences per second being offered to the system. And what delays do we see? Now, in this case, we start to see that Storm's maximum latency is starting to increase, and indeed, under quite high load, the maximum latency for Storm can get significantly bad. We start to see these peaks, although its minimum latency is still very good. But its throughput is very much lower now. Its effective throughput is significantly lower than both Dragon and Heron. Dragon is still a bit lower than Heron, but does keep up with it. These thick black bars here don't show us all that much, but when we look at the CDF here as the inset, you can sort of see that there are different grades in Dragon. There are different, very distinct steps, if you like, where a token either or a word either has experiences this kind of behavior or a different kind of behavior as it goes through this topology. So looking at these numbers, you see Storm still has its sort of sub-millisecond latencies, but its maximum latency is quite large. The maximum latency of Dragon is quite small compared to the others, and it does have still a minimum latency that's very low as well. So it does make a very good comparison there to the others. Its mean latency is comparable to Storm in this case, which is kind of half of that of Heron. So we sort of see from these results that Dragon doesn't do too bad as a sort of first implementation of a stream processing engine compared to these competitors, which have been around for quite some time now, optimizing and building better and better approaches to the way that they do processing, which was quite a good outcome for us. The related work, there is there are people measuring the performance, not just of Apache Storm and Heron, but also of Flink, which we are intending to do. We're doing at the moment, in fact, and Spark, and so some of the other rivals in the space of providing stream processing systems. Various kinds of studies over the time that have done more or less the same as what we have done in measuring the throughput and the latency and other things such as the fault tolerance, checkpointing, and so on. And we are in the process of implementing checkpointing and other fault tolerance in Dragon. So in conclusion, Storm has sub-millisecond latency, which is very, very good, and it achieves that through using very high-performance non-blocking queues, and by ensuring that queues are never really, never start to fill up. And so it's good for ultra-low latency applications like high-speed trading. But the only way to do that really is by throttling the input a lot. So its effective throughput is actually quite poor compared to the other two systems we compared to. It can be quite low. And under high load, it can start to exhibit some spiking, quite a bit of spiking in its latency. Heron provides the highest effective throughput with respect to the offered load, and gracefully becomes unstable as the throughput exceeds its capacity. It's a bit better at becoming gracefully, becoming unstable, if you like, than what Dragon was. Dragon is a good all-rounder, though. Sort of, it sits in the middle of this rock curve, if you like, and it has lower latency than Heron and better throughput than Storm. So it also has the lowest maximum latency of all three under high load conditions, which I think is interesting. And we did observe that we could remain stable and an effective throughput of roughly 9,500 sentences per second, whereas with Heron it started to become it couldn't remain stable at that point. So we managed to achieve a little bit higher throughput. And that is the conclusion to my talk. And I hope you enjoyed reading through the paper. And if you do want to talk more or ask some questions, by all means, please contact us. And indeed, if you want to work with Dragon in any way, we'd be more than happy to help you. Thank you very much.